Welcome to example 4 of 9.4. We're looking at sum of an infinite geometric series. Couple things to look at on the side. We have a geometric series defined here. A can't be 0 because if your first value is 0, then everything is 0 no matter what you multiply it by. The other thing is we know it will converge if and only if r is between 0 and 1. And if it does converge, we can find the sum with that formula right over there. Now, logic is that if it's greater than 1, if a common ratio is greater than 1 and you're adding constantly, then you're basically going to end up adding to infinity. But if you're adding something that's getting infinitely small, again, you're multiplying by something between 0 and 1 to get your next number, then that's where you'll have a convergence, and you can find it by that formula. All right, let's look at A. Notice here we have a common ratio of 0.75, and looking at that, if I plugged in a 1, this would just become 0.75 to the 0, which means that the first term is 3. Now, with that said, let's write a couple of these things down. So my common ratio is 0.75. My A, or A sub 1, would be 3. And now if I wanted to figure out whether it converges or diverges, I look at my R. It is between 0 and 1, right? The absolute value of R is less than 1. So I do know that this thing does converge. And if it does converge, it converges to, in this case, it would be, let's see, 3 over 1 minus 0.75. And that would be 12. All right, let's go to part B. Part B, notice that I have the definition written a little bit differently because it starts with n equals 0. Regardless, if I plug in that 0, it gives me my first term. And that means my first term is actually 1. So I'm going to rewrite this. Well, not rewrite it, but I'm going to write down some of the stuff. So I know my R is negative 4/5. And my A would be 1, right? Again, because if I plugged in 0 here, that would just become a 1. So that's my A. That's my first number. And or A sub 1 if you want to write that. The textbook just writes A. And R here, if I plugged in a 1, then that would mean it's 1 times negative 4/5, right? Because it would be negative 4/5 to the first. And so my R is negative 4/5, and again, 4/5 is between 0 and 1, the absolute value of it, right? So I can go ahead and say it converges to 1 over 1 minus negative 4/5, which is 5/9. Part C, I can see that my common ratio is pi over 2. My A, if I plugged in a 1, would be pi over 2. But pi over 2 is greater than 1, so I know that this diverges. Let's go to part D. Notice part D, the series is written out in its discrete form, right? 1 plus 1/2 plus 1/4, right? It's actually writing out the discrete elements each term. I know the common ratio you can see is half, and A is 1. And so if I wanted to write this one out, we do know it converges because R is less than between 0 and 1, so it converges to 1 over 1 minus half, and that equals 2. And that's it. One other thing I want to show you that was kind of cool that has to do with D is this. So if I have, let's say, a square, right? I know that square is equal to one whole square, right? What if I were to chop it up in half? So I know half plus then a quarter plus an eighth plus 1/16 plus 1 over 32 plus 1 over 64 plus 1 over 128 plus 1 over 256 plus 1 5/12 plus 1 1024ths, right? So here's your half, your quarter, your eighth, your 1/16, your 1 over 32. You can tell that I can keep chopping those little sections into half and half and half, but this would all equal 1. And so, if I then put another square and added it, so that's this part right over here, right? This represents this part. So that's a pictorial proof, actually, of an infinite geometric series. So hopefully that was kind of interesting to you guys. Kind of cool where you can convey all of this with this one little picture here. All right, I'll see you guys in the next one.